For 1 hour, they said, yeah.
So, yeah, shorter than the original.
Yeah, probably, yeah.
With data just coming out of the...
Yeah. So. Aha. Okay. Yeah. But does this work? Or it does, okay. This is until 4, yeah. Then there's a coffee, half an hour coffee break, I think. Yeah. 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 Carmen, do you know if Wilfried is here today? Wilfried, is he here today? Wilfried?
I haven't seen him, but I wasn't there.
No. Yeah, no, maybe Jared wanted to see him after, if he's here. He was here yesterday, but let's see if he's here. Okay. Yeah. Okay. So I should start, according to Brent. So welcome everyone to this session on the role of non-CO2 greenhouse gas emissions in mitigation scenarios and climate change. And I thought I would start with a short recap of where we are sort of in this. As we talked a little bit here before, I think the non-CO2 greenhouse gases have been treated a little bit, I mean, it has not at all had the same attention as the CO2. So, and I think it also shows actually in this meeting where we only have this session that is dedicated to the non-CO2 greenhouse gases. And it's contributing to at least 1/3 of the warming. So I think this is something that we need to improve. And just a very short recap here. We have the global non-CO2. I think the bottom-up and the top-down budgets at the global level, we are kind of getting closer there, not least thanks to the Global Carbon Project and the work that has been done there. But we still have a lot of uncertainty at the regional and sectoral levels. But we have some hope from the recent advancements in different measurement technology, not least from the satellites. We have quite some work done on technical and to some extent also for the structural mitigation potentials. What we still need to get better at is covering also behavioral and institutional barriers for non-CO2 mitigation. When it comes to the atmospheric chemistry, I think we have to make sure that we cover all the non-CO2 species. We have one speaker today who will address such a deficiency. And the atmospheric chemistry is obviously very complex, and there is still quite high uncertainty on the sinks, for example, for the hydroxyl sink for the methane. And how these also might be affected by different changes in the atmospheric chemistry. When we see also transitions away from fossil fuels, for example, and so on. And last but not least, we also have the governance and policies, in particular how to regulate short-lived versus long-lived gases, which is something that Daniel here will address later. And this is, of course, very crucial for because of non-CO2's contribution to warming, in particular in the short term. So let's go to the list of speakers. And the first speaker, so the first 3 speakers will address more emissions and mitigation potentials at the global level. And then we have, and then we have Laura Wilcox, who will talk about aerosol emissions and how this has been omitted previously in the non-CO2 budget. And then Daniel will finish with the social cost of methane in a scenario context. So let's start with Yang Wu. Beyond decarbonization, deep mitigation of all greenhouse gases towards 1.5 and 2 degrees future.
Hi everyone, I'm Yang. I'm a scientist at the Pacific Northwest National Laboratory in the US. In this talk, I'm going to share some recent work we've done that look at the deep mitigation scenarios that focus on all GHG emission reductions, and especially for the role of non-CO2 GHGs. In the recent IPCC Working Group 3 report, we can find that non-CO2 GHGs, namely CH4, N2O, and F gases, have contributed to roughly 1/3 of the growing GHG emissions in the last 30 years. All of them are showing a growing trend, especially F gases. However, it's clear that stabilizing climate change well below 2 degrees and towards 1.5 degrees requires deep mitigation of all GHGs, including both CO2 and non-CO2 GHG emissions. Here in the same report, we can find that when achieving net zero CO2 globally, the magnitude of non-CO2 emissions vary across different scenarios shown here. So reducing non-CO2 emissions is very important because eventually we will need carbon removal technologies to offset these residual non-CO2s, and some of them can be very expensive. To reduce non-CO2s, the first step is understanding how to model non-CO2s and represent them in the model. The challenge here is that non-CO2 emissions come from different sectors and processes. Some of them may be relevant to fuel combustion. So you cannot use the fuel consumption data and emission factors to simply calculate these emissions, such as F-gas in cooling sectors. On the other hand, many CO2 and non-CO2 emissions are intertwined. So your model needs to have a multi-sector structure and sufficient details to represent this kind of multi-sector dynamics. So here, what we incorporate is the latest non-CO2 emission data from the Global Non-CO2 Mitigation Report from US EPA. It covers all major sectors and gases. All these sectors are already represented in the global change analysis model that we developed. So it is straightforward to capture the historical trends and emission factors, and which will ultimately drive the future emissions. Mitigation options here are parameterized by a marginal abatement curve. This curve tells you how much emissions can be reduced at each level of mitigation cost you are willing to spend. The EPA report has these max by sector, by gas, by region, and by year. So our non-CO2 mitigation options in GChem can capture these kind of details. Additionally, we also consider the effect of technological change. So when technology is cheaper and more efficient in the future, the MAC will shift to the right, meaning that you can achieve higher emission reductions with the same level of mitigation cost, here characterized by the CO2 prices in the model. So after we improve the model, now let's talk the research question. Here, we try to understand the role of non-CO2 mitigation in deep decarbonization scenarios. Specifically, we want to answer for the same climate targets. To what extent non-CO2 mitigation can share the burden of CO2 reductions? And for the same CO2 mitigation pathway, how much additional climate benefits can be achieved by comprehensive non-CO2 abatement? So here we developed 90 scenarios pairing different CO2 mitigation trajectories and different level of non-CO2 abatement assumptions. For CO2, we model linear reduction trends towards different net zero years starting from 2030 to 2100. And for non-CO2s, we look at no reduction or fuel switching only or comprehensive reductions that I will cover more details later. We model these scenarios in GChem and look at their climate results and see what combination of these scenarios can achieve the 1.5 degree and 2 degree targets. Here, the difference between 2° and 1.5° pathways is that they assume different level of negative CO2 emissions after net zero, which this level is consistent with IPCC assumptions. So in this chart, each dot represents one scenario with different year of net zero CO2. Here you can see all scenarios just assuming CO2 reduction only while holding non-CO2 at the same level of reference. And we will find that there's no way to achieve 1.5° on the left-hand side, even reaching net zero CO2 by 2030. When allowing the non-CO2 emission reductions from fuel switching, which we call the CO2-driven Ghg abatement, 1.5° is achievable, but only if we can reach net zero CO2 by 2032. However, if we fully consider non-CO2 reductions from both fuel switching as well as those abatement measures that are not correlated with fuel switching in the energy sectors, we can see 1.5° is achievable if CO2 can reach net zero by mid-century. So in summary, when looking at these three lines side by side, we found that when fully considering non-CO2 abatement, the timing of net zero CO2 could be 2 decades later to achieve the same temperature goal compared to those only considering CO2 reductions. Next, let's look at detailed emissions and climate results. Here in the reference, both CO2 and non-CO2 emissions are growing rapidly. And when reducing CO2 alone without any non-CO2 reductions, you see this is impossible to reach the 1.5 targets. When considering non-CO2 reductions from fuel switching only, we see that non-CO2 emission reductions can be roughly 40% in 2100, making 1.5° targets barely achievable, but just in theory, if you look at the CO2 trajectories on the left-hand side. And on the under the comprehensive abatement case, non-CO2 reduction can be about like 60% in 2100. So our central 1.5° pathway in this red line is much more reasonable. Here, CO2 reductions can be reduced by into net zero by mid-century, consistent with the trends we were seeing in the recent literature. So after we look at the big picture, the question is what exactly happened to the non-CO2 emissions and what non-CO2s are reduced? As you can see here, non-CO2 emissions are primarily from fuel extraction, industrial process and cooling, and agriculture sectors. CO2-driven mitigation actions will retire coal and reduce mining emissions, but has limited impacts on other sectors. Additionally, including non-CO2 abatement measures, you see that the cooling emissions can be heavily reduced, right, in these yellow parts. Another angle is looking at the emissions by species. So you see that CO2-driven mitigation could reduce methane emissions in the energy sectors, and the comprehensive Ghg emission abatement will further reduce emissions from the HFCs in the bottom parts, which are known as like long-lived climate forcers with very high global warming potentials. Actually, here, let's talk a little bit more about these F gases. You know, like HFCs are used in various industrial and building applications, such as refrigeration, air conditioning, aerosols, and even fire extinguishers. But in fact, these sources have many very cheap abatement measures as simple as leakage repair. So these affordable measures can reduce over 90% from these F-gas emissions. And from this chart, you can clearly see the difference between the second and third panel here. So spatially, since many of those F-gases emissions are related to industrial processes and building demand, here we found that greater non-CO2 reductions achieved in those growing economy, you can see, such as China, Brazil, South Asia, and Africa. And finally, after talking about where and how we can reduce non-CO2 emissions, let's revisit the emissions that are hard to reduce. Here we found agriculture stage 4 and N2 emissions actually barely affected by the abatement measures included in our analysis. So one future direction, or probably other talks in this section, will look at are those like innovative approaches and mechanisms that can help us tackle these residual emissions. I will stop here at the summary page, and finally, I just want to acknowledge all the co-authors in this analysis from our PNL lab, as well as US EPA. And I'd like to thank you for this opportunity to present this work here. With that, I'm happy to take questions. Thank you.
Yang Wu with us?
Yes.
Yes, hello.
Hi.
Welcome.
Yeah.
So, do we have some questions? Yeah. I think Matthijs has.
Yes, thank you for a very nice presentation and nice paper. I also read that.
Maybe say your name. So
sorry, my name is Matthijs Harms from PBL. I was wondering, the US EPA MACs hardly or not at all, I think, includes a technological change. Is that? Do you know that if that's correct? And if so, did you do any checks or I don't know sensitivity analysis or looked at? Sorry. Okay. Okay. Yeah, and then we'll probably hear about it in the next presentation. But did you consider that and try to see what the implications could be if you would include more technological progress, but maybe also removal of implementation barriers and so on?
Oh yeah, that's a good question. Like, what technology change is actually one of the major like parameters we put in the model, and that's a huge improvement here. And very nicely, EPA data includes some of the technology change assumption here. But in our paper, actually, we did additional sensitivities related to the technology change assumption. We actually have some charts showing like low technology change, high technology change versus the central case I present today. So in general, it can affect roughly, I would say, 0.2 degree difference if we consider the lowest versus the highest technology change. Sorry, I don't have like too many, I don't have the slides by hand, but if you can look at the paper, that will be much more clear about this kind of technology change assumption like we made in alternative case.
Okay, thanks a lot. Oh, we'll have another look.
Yeah.
More questions for Yang Yu? No? Stefan?
Hello, Stefan Frank from IIASA. Thanks a lot also for this very nice presentation. I was wondering, what is the reason that in GCAM the agricultural sector is hardly impacted by the carbon price on non-CO2 emissions? Or the reason for the very limited mitigation potential?
Okay, yeah. It's actually like I said, it's limited mitigation potential is really compared with other sectors. You can see much more like obvious reductions in those energy sectors. And actually, if we would not include any mitigation potential at all, the emissions from agriculture sector will actually increase because like this agriculture productivity and all the stuff is highly linked to the demand growth and the population growth. So in GCAM, we have this fully coupled like agriculture activities with all the other economics and also even the bioenergy production. So if in a mitigation scenario, you don't do anything in the agriculture, it will be like even much higher. Here, we just basically have this kind of mitigation potential in place so we can barely keep the agriculture emissions not increase. I would think this is actually a good signal here. But definitely, if you also look at the, like, for example, MAC data, marginal abatement curve in the agriculture sector is fairly small compared with those F gases. I guess it's really just these technology features, you know, like you want to stop like methane from beef, like from cow cultivation, that's really hard and it's very expensive. So yeah, I guess this is both like we have the model details here that drive this emission grow in the future, and also it's really in the real world there's limited like mitigation technologies available in this stage. But I'm sure like there will be like more like cheaper technologies in the future.
Okay.
Did this answer your question?
Thank you very much. I think we should move on. Thank you, Yang Wu. Please stay with us. So, can you take this?
Sure.
That's all right. I can introduce myself. You got? Can I use the clicker too?
Yes, please. And I will show you this when you have 2 minutes left.
Oh yeah. Okay. The yellow card. Hi everybody. I'm Jared Creason, U.S. EPA, in the Climate Change Division, and I'm presenting projections of global baseline emissions and mitigation potential for non-CO2 GHGs under alternative scenarios. This work extends and expands on our global non-CO2 projections and mitigation report from 2019, which you just heard about. Again, how many of you have used or are familiar somewhat with the EPA max? It's a fair number of hands. I'm going to go a little fast in the interest of time. Yes? Yeah? Okay. So I'm going to skip this. We've been doing this since the 90s. Many modeling teams use EPA max. There's CGE models that use our data, also integrated assessment models. And the max really represent economic mitigation from a fixed activity driver baseline. So in a typical application, such as Yang's, modelers will calculate their emissions endogenously and apply the max in percentage terms. So in this research, we're going to break that mold a little bit, and we calculate 5 separate baselines for the SSPs and abatement that is specific to the SSPs. And then we look at sensitivity analysis by varying the technological change parameters in a way that we think is consistent with the SSPs. EPA max, as you heard, have a learning rate and a abatement efficiency improvement parameters, and we're going to change those. We also have high and low learning rates for high and low income countries in SSP4. All right. So familiar graph. I think I've seen this graph about 4 times in the last 2 days, but this is from the IPCC AR6. The gray segment of the histogram is non-CO2s. And non-CO2 emissions remaining at the time of net zero really determine the amount of additional negative emission energy technology or direct air capture or LULUCF sequestration that's required to meet a zero GHG goal. So it's really important in these net zero, the max sort of become or the non-CO2 gases sort of become the sticking point. Next, talk a little bit about baseline. This data comes from the IIASA SSP database, and it shows the size of the circles represents the amount of methane emissions in 2050. The horizontal axis is GDP per capita. The vertical axis is energy per GDP or energy emissions per unit energy on the right-hand side. Kind of a standard Kaya decomposition. But you see some variability with energy intensity of GDP on the left and less variability with emissions intensity of energy on the right. Interestingly, most of the SSPs, SSP2 is described as middle of the road, but most SSPs exceed SSP2 in non-CO2 emissions from 2 to 25%. Only SSP3 has reduced non-CO2 emissions relative to SSP2, the baseline. That makes it hard if we're going to get to net zero, and I went to there. This slide shows a sector breakdown for industrial energy and waste. And what I want to point out here, there's no pointer, okay. What I want to point out is that the industrial sector, which is shown orange, emissions are smaller both in percentage terms, the size of the pie, you can sort of see that, in SSP3 compared to the other cases, and also in number, in actual quantities. Energy emissions and waste emissions, or blue and gray, respectively, are roughly consistent in percentages, but highest in quantity under SSP 5. The other differences between the sectors, 1, 2, 4, are all within 10%. There's really not much movement in the baseline data. So we're going to look at our max and the assumptions on learning rates and the reduction efficiency improvements. This chart shows the assumptions that we use. These are for 2050. And you can see SSP2, the values are in bold. Those are the default values from the 2019 report. All right. And basically, this is sensitivity analysis. We in some cases doubled them for SSP 1 and 5, and be kind of consistent with the narratives that the world is working together in a more connected way than in 2 and 4. 2 and 4 have less. I'm sorry, 3 and 4 have lower values. And you can see there's a reduction rates for mature and nascent technologies, and the learning rates for high and low income countries in SSP4. You saw this slide earlier. This is sort of the anatomy of our marginal abatement cost curve. The marginal abatement cost curve is shown as the curvy blue line, and it starts with negative cost emissions. In this case, it's about 8% of the total emissions. And then you're into the middle zone there where increasing abatement is available at increasing costs. And that curve goes vertical at the maximum abatement potential. And it's sort of the asymptote of that exponential function. And then the difference between maximum abatement and total emissions is what we call residual emissions. And those cannot be abated under available technology. So now we're going to look at some results. This graph shows separate marginal abatement cost curves for the 5 SSPs, and the graphs above and in the bar charts below. So if you look at the purple line up here, that corresponds to the SSP5 case with total emissions of about 9,000 metric tons, and you can see the breakpoint where the residual emissions began. SSP3 has the lowest mitigation potential. SSP5 has the highest. SSP2 is right in the middle. The lowest residual emissions occur in SSP1, actually, and SSP5 is second. SSP1 and 5 offer higher learning rates, right, and greater efficiency gains, and those, in our analysis, overcompensate for the increases in emissions in SSP5, for example, and 1. So this nominal ranking is true basically for every sector, but I'll click through them. I'm going to skip the energy sector. I'm going to go right to the industry sector. It looks a little bit different. SSP3 and 4 offer less abatement relative to SSP2, not because of the shape of the curve, but mostly because of the baseline levels of emissions. you can see the percentages there are very consistent, around 23%, whereas the residual emissions in SSP1 are 16% lower than baseline, and residual emissions in SSP5 are 10% lower than baseline. All right, waste sector, a lot of similarity between SSP2, 3, and 4. This looks a lot like the energy curve. Residual emissions in SSP1 and 5 are about 28% lower than baseline. So what have we done? We conclude that the changes to the parameterization produce generally bigger changes in residual emissions than the SSP baselines. SSP 1 and 5 are characterized by lower barriers to adaptation because of the convergence of technology in those scenario descriptions. And maybe that's more like a world where countries are all working together to reach a net zero target. So maybe we should be, adapting our MACs to fit that scenario as well. This work is exploratory, but it seems to suggest that this more detailed approach could result in better estimates. Thank you very much.
Herwan McJohn from PNNL. Thanks for a great presentation. Can you comment a little bit about CO2 and non-CO2 interaction? Specifically, I'm thinking as you reduce emissions, you will be using much less coal, gas, and oil. And so there's associated activity with methane emissions. Or as you reduce more emissions, you will be reducing consumption of beef. So not only the MAC curves come in, but also the total size of the meat pie, so to speak, decreases.
Yeah, so we don't have drivers in the MAC model. The only way that enters is through the SSP baselines.
Thank you for a very nice talk. I have a question. You did not consider agriculture, I think, in the study. So why didn't you consider agriculture, and do we have plans to sort of adopt a similar approach to agriculture emissions?
Our agriculture model is different in the EPA MACs. It's based on a biogeochemical gridded crop model of the world. So it's difficult. Implementing technological change is different in this case. We're currently revamping or doing a new set of model runs with the team from Colorado State, the DECENT model, and we hope to incorporate that soon. But it's we left it out of this analysis because it's just still in the works.
Thank you very much, and we should proceed with Matthijs.
All right. Thank you for having me at the Scenarios Forum. Today I'm going to tell you about something about uncertainty in non-CO2 greenhouse gas mitigation, and we've analyzed that by basically creating a range in marginal abatement cost curves and assessing that with an integrated assessment model, in this case the image model. So there's no question about the relevance of non-CO2 mitigation. It has been shown quite often that it's obviously, and also here, needed to reach ambitious climate targets, and also in many studies that it's obviously reduces the overall cost of climate policy. But as always also has been said, you can argue that there's been relatively little attention, given that it's roughly 1/3 of total emissions, and also the complexity, the many sources. So maybe even not many people here in this room, it keeps baffling me. And this mitigation information is, however, used by integrated assessment models and thus feeds into into the assessment reports, into the climate negotiations. So it does have a large role, and it is in the form, usually, almost generally, in marginal abatement cost curves in integrated assessment models. But there are several problems with these MAC curves. First of all, they're produced by a very small number of groups who are basically all represented here. Long-term MACs, which we obviously need for long-term projections, are quite rare, and sometimes also used inconsistently, for instance, when implemented double counting of certain factors. And we also found that the MAC data used by models is often, here I say more than 10 years old, can also be more than 15 years sometimes, still using Lucas et al. From 2007 or so. And then unavoidably, models also use one middle-of-the-road estimate, just the MACs that are available, and here we try to solve that basically. And I'll also show in this presentation that the uncertainties that are inherently high but are hidden actually in these models can have huge implications for climate policy feasibility, climate policy costs, and also the need for CO2 mitigation in the form of carbon budgets. So in this study, we have a first systematic bottom-up approach to assess uncertainty in long-term MACs, and also long-term non-CO2 mitigation and costs. And we do this by developing basically optimistic, pessimistic, and default MACs, so really creating a range there. And we have assessed this in the image model, with the image model, in an SP-based scenario setup, also to take into account uncertainty associated with activities. So this is an alternative to what is normally done to assess the uncertainty related to non-CO2. Usually people have a look at the, for instance, the databases for the assessment reports, and then see what the effects of on the carbon budget are related to non-CO2 uncertainty. And there, for instance, you can see in the 1.5 special report in AR6 that it's roughly 250 gigatons of CO2 in both directions, and that's actually huge. So considering that, in a 1.5 and 2 degree scenario, we have a budget of 400,000 gigatons left. And in this case, it's also, with this approach, that other approach, it's also unclear what underlies this huge range. And here we try to solve that as well. So on the method, we basically use the approach that we also used for a 2019 paper, but here adding optimistic and pessimistic MACs based on a Monte Carlo analysis where we vary the underlying parameters that build up the MACs. And we added more literature, basically everything we could find on individual studies, on individual measures. And here the equation is not really important, but these parameters, they basically represent technical applicability, so how much is reduced if you implement a certain measure. Sorry, that's the second one, reduction when applied, but also applicability is where can you apply a measure, which part of the baseline can be reduced. Also non-technical barriers, also the overlap between measures is of course important. If you have a measure, then the second one has diminishing returns, and also technological progress, so we have all sorts of assumptions there. We have applied this full Monte Carlo analysis to the agricultural sources only, because there these are hardest to abate, these are also most uncertain, and we looked therefore also at these in most detail in this prior study. And the ranges are based on literature, but also some insights from the Ghgs team. We had some discussions there. And for the optimistic MACs, we also, in some cases, added some additional measures that haven't proven themselves fully, but fit an optimistic MAC, we think. And we did 1,000 runs, and then the MACs are the 50th and 59th percentile. And then you get something like this, with the whole range, and then the upper and lower MACs. And here you can see, for instance, that roughly the most optimistic MACs have twice as much potential than the pessimistic MACs for agriculture source. For all the other non-agricultural sources, we had a much more simpler approach, namely changing the maximum reduction potential, also based on literature as much as possible. In here, usually there is, even in a pessimistic case, a relatively large reduction potential you can already know based on current studies. So, yeah, then moving to the results. First of all, the MEC uncertainty translates into non-CO2 reduction uncertainty when you put it through a whole scenario analysis. And here you can see that. So here on the x-axis you have the two scenarios, 2 degree scenarios and a 1.5 degree scenario. And on the y-axis the reduction in the CO2 equivalents. And then obviously you hope to have as much reduction as possible. So green is on the top side, optimistic, and yellow is the effect of the pessimistic MEC. So in a 2 degree case, that's the reduction we projected was 40% to 85%. In a 1.5 degree case, the net reduction was 54% to 54 to 65%. But note that this was only the difference between a default case and optimistic case, because we found no feasible case with a pessimistic MEC to reach a 1.5 degree scenario. So that already shows the importance of non-CO2 reduction. And here a bit more complicated maybe, but we also have a short look at the forcing differences between optimistic and pessimistic in a 2 degree case, just to show you the influence of the different gases. And there you see in watts per square meter that methane 0.08 is the largest. And for instance, F gases is quite low. This reflects in principle already the influence that these gases normally also have, but F gases is particularly low, and that indicates that even in a pessimistic case, there's already quite a lot of F gas reduction. So the uncertainty there is quite small. So that was just to indicate. Then the climate policy cost. Here again, the same sort of graph, but then on the lower side is optimistic. Of course, you don't want to have too high costs. The values here are not really important. It's the discounted cost over the whole century, but these differ per model anyway a lot. But here, the relative difference between optimistic and pessimistic is most important. So you see in a 2 degree case that you have a 32% higher cost moving from pessimistic to optimistic, from optimistic to pessimistic, and 59 in a 1.5 degree case where it's difficult anyway. But again, this is only the difference between default and optimistic, and you basically can say no matter how much money you throw at it, in a pessimistic case you will never reach 1.5 degree. Yeah. And then the carbon budget. Here, same sort of graph. The upside is of course, so you want to have the largest carbon budget as possible. Then we found a difference of 260 gigatons between optimistic and pessimistic in a 2 degree case. But when adding, for instance, the SP1 activity assumptions, we found an additional 180 gigatons of CO2. So I would say coincidentally, this is actually quite similar to the top-down approach I showed earlier. But here we understand where it comes from. And then, but here we have an additional case that when we have the SSP3 activities, then 2 degree would even be out of reach. So pessimistic plus SSP3 activities, by far we can't reach that scenario by far. So therefore, showing how important that is. So to summarize, first of all, non-CO2 MEC uncertainty can have massive implications for climate policy feasibility. A 1.5 degree scenario could be out of reach. Non-CO2 relative reduction could vary by a large number. Carbon budget, same. Climate policy costs could vary considerably. But uncertainty is even larger when considering human activities. So we find 180 extra gigatons of CO2 when you have SP1 assumptions, and we say we think that a 2 degree scenario will be out of reach with in an SP3 world and pessimistic assumptions. Last discussion points. First of all, it's important to realize what is this uncertainty, what does it even entail? And partly this is something that can be bridged by human activity, so it's just basically, the efforts that governments would have, you could bridge, for instance, or you could overcome implementation barriers if you would try hard enough. But largely, we think it indicates really technical uncertainty. So you could find yourself at the bottom of like in the pessimistic side, and there's not much you could do about it. Also good to know that there's lots of assumptions here. We try to use literature as much as possible, but if we don't know a certain value, but we think there's large uncertainty, we just chose a large delta between high and low to compensate for that. But then there is really uncertainty there. Also good to know that we didn't include wetlands. It's a factor that can be huge, can have a huge impact, but also towards the positive side. In that sense, that's just basically good to know when implementing these MECs. We didn't include that. Yeah, and F-gases seem to be a small factor. Okay, and if you're interested in using these MECs, they're now available via this link. And with that, I'd like to thank you.
Thank you. Very interesting talk. I was thinking here in the image model, if you sort of, I guess you price methane emissions basically, and you, for that reason you reduce emissions. You have a price on the methane emissions, but do that price also trickle through to the consumer products, and you get a reduction in demand as well? And is that taken into account in the scenarios?
No, it doesn't. That's really one as on our wish list, something we haven't included yet. Yeah, and it could mainly be important. Yeah, it could definitely be important for fossil fuels, but there's a phase out for a large part anyway. On the agricultural side, we didn't include it too, but there could be reasons not to do it, because you could accept, it could very well be that the world wouldn't accept that food prices would go up. For meat, I would personally do it, but that's why it can also be considered unrealistic. And the carbon price or carbon equivalent price is something that sort of represents the ambition that you have in climate policy. Doesn't necessarily mean that you actually have a price, but yeah, true. I think that there could be some improvements there. Yeah.
Hey, John from PNNL. Great thorough work. Monte Carlo approach, I really like it. I think this is going to be preaching to the choir here. This shows how much interest they have in non-CO2, given 15 out of 300 people in this room. But as you show, it's so much important. They talk about carbon budget, decarbonization, carbon management, but really it's greenhouse gases, and you show that 1.5 degree in pessimistic, it's not even feasible. Sometimes 2 degrees is not even feasible if it's SSP 3 and pessimistic. We need to tell the main hall guys, how do we communicate? Why is the climate modeling community, impacts community so focused on carbon budgets when it's GHG? So you don't actually have to answer this, but it's my rant to the bigger group.
Oh yeah, I thought you were going to answer this, but what's the next question? Or
kind of. So I had this comment, and I didn't want to just make a stupid comment, but rather maybe have a question. But the reason why we are concentrated on CO2 is because it's a long-lived climate class, right? So this kind of reduction in methane or other shorter-lived greenhouse gases, it's a short-term intervention, and so I'm actually writing a paper right now that when your greenhouse gas is short-term and therefore kind of delay decarbonization further, that's actually from a moral philosophy kind of standpoint problematic, because you're moving that burden to the future generations. So I agree, I'm in the non-CO2 session, I think it's important, but there is also a reason why we concentrate on CO2.
yeah, but I mean, both good points. I totally agree. Preaching to the prior, and it's. I totally agree also that you don't want to focus too much on non-CO2. It's cheaper, and then not do something. And it should be additional in all cases. But having said that, many studies also show that like you said, that you need it to reach targets, and it's a no-brainer. It's cheap and it's needed. So if we can make it additional, then. But I totally agree that it's so weird that there's little attention for it. It's not sexy, apparently. I think another reason is also that it's not related much to the energy system, which gets a lot of attention from energy modeling groups because it also has other reasons, of course, for society. Here it's just mainly waste, but very important for climate. So, yeah.
Thank you. And maybe I can also just comment on that last comment that it's also important in the short term because to avoid temporary overshoots that could potentially spiral off into. Yeah, we are. That's where we are moving now. So we will listen first to Laura Wilcox on rapidly evolving anthropogenic aerosol emissions induce strong and regionally heterogeneous climate impacts on the way to a net zero world.
Hello, I'm Laura Wilcox from the National Centre for Atmospheric Science at the University of Reading, and I'm going to talk to you today about the potential of rapid changes in anthropogenic aerosol emissions to cause strong regional climate impacts in the near future. I'm giving this presentation on behalf of my co-authors Gita Prasad, Bjorn Samset and the wider regional aerosol community. I'm going to start with a global picture where we see large forcing and uncertainty due to anthropogenic aerosol emissions. On the left here you can see effective rates of forcing, and on the right the equivalent change in global mean near surface temperature from a number of anthropogenic species taken from the IPCC's Working Group 1 report for AR6. At the top, you can see greenhouse gases such as CO2 and CH4, and the bottom bars in purple show the aerosol contribution. Over the historical period, aerosol emissions have increased, so we see a negative effective rate of forcing, averaged over all species, which leads to a cooling effect in temperature, which has offset around a third of the greenhouse gas-driven warming over this period. What you can also see in this figure is the large uncertainty associated with our aerosol forcing and our aerosol temperature response indicated by the confidence intervals on these bars. And this position of aerosol as the largest uncertainty in anthropogenic forcing climate has persisted through all of the reports of IPCC. As we go into the future, we expect aerosol emissions to decrease as we become more concerned about air quality. So near future contributions to global temperature from aerosol are likely to be warming, so in addition to that greenhouse gas driven warming. And aerosol in the future becomes relatively more important in our Paris compatible scenarios, so SSP 126 and SSP 119. You can see that in this figure here where we're looking at scenario total warming in 2014 relative to the present in grey, with the aerosol contribution shown in purple. So aerosol is contributing a warming in all scenarios except SSP3, where it continues to increase, and accounts for almost half of the global temperature change on this timescale in SSP 119. But aerosol is more than just an offset or a contribution to global mean temperature because of the way that it's distributed. So wherever you are in the world, your aerosol is going to look different. And you can get a sense of that here in this snapshot from the GS5 model, where you see aerosol species in different colours. So if you're in Asia, for example, you're going to have a lot of industrial aerosol, a lot of sulfate, whereas if you're in the southern hemisphere, your aerosol is going to be coming more from biomass burning, and will be these green colours here showing you the smoke. And this diversity in aerosol regionally and in terms of species is also seen on climate timescales, and is reflected in aerosol rates of forcing. So if we look at aerosol forcing in our CMIP6 models for 2014 versus 1850, you can see largely a negative forcing, as we saw in the global mean, but it's much stronger over Asia, where most of our aerosol emissions are today. You can also still see large forcing over North America and Europe, and a lot of uncertainty about the forcing in the southern hemisphere, where both aerosol emissions and the response to them are more uncertain. And this picture looks very different to what you'd see for greenhouse gases, where you'd see a very uniform positive rate of forcing. And these differences in forcing pattern are reflected also in the climate fingerprint of these two species. So I'm showing you now on the left the temperature and precipitation fingerprint of greenhouse gases, and the same for aerosol on the right. And you can see these look very different, particularly for temperature. We have cooling and warming from aerosol depending on where we are, and the magnitude that temperature response looks very different, again depending on where we are, where the temperature response to greenhouse gases is more uniform. And the same is true for precipitation. And this is partly due to the differences in the pattern of the forcing, but also due to the differences in the way that these different species affect the climate. So the temperature fingerprint from greenhouse gases is largely driven by thermodynamic response, whereas the response to aerosol has a large dynamic component. And that's going to become important as we go into the near future, as I'll hopefully show you later. So far, I've shown you that your aerosol is going to look very different depending on where you are, and that aerosol is present in high amounts over densely populated regions. Aerosol can have strong effects on climate. I've shown you a fingerprint earlier, and I'm now showing you in the middle row here a 5-day maximum precipitation response to future aerosol reductions, where we see an increase in extreme precipitation over India and China, and we see this dipole pattern over Africa in the middle, associated with the shift, the West African monsoon and the ITCZ. We also see here changes in extreme precipitation over Europe, where aerosol emission changes are actually quite small for the time period that I'm showing you, so 2031 to 2050. And that's because the regional nature of aerosol changes mean that they're also very capable of driving teleconnections, and are thus important far from their emission sources as well. And those teleconnections might look like Walker circulation adjustments, for example, in the tropics, or changes to Rossby waves in the mid-latitudes. So as we go into the future, we'd expect most of our aerosol changes to be over Asia and over Africa, but that's not necessarily where we're going to see the large impacts. At the moment, we're seeing large, rapid changes in anthropogenic aerosol, particularly over Asia, where in recent decades we've seen rapid reductions in Chinese emissions and Chinese aerosol burden, in contrast to continued increases over India. And these are patterns that may continue into the future or may change. And this is the kind of thing that we want to explore with scenarios, because these strongly localised changes in our aerosol are going to affect local temperature and also the local circulation and local precipitation, such as those extreme changes I showed you in the previous slide. And actually, in the SSPs, we did a pretty good job of exploring the range of aerosol emission uncertainty. So I'm showing you here a global time series for some aerosol species in the top row and CO2 in the bottom. And we have our SSPs in colour here compared to our RCP range in grey. So you can see for all our aerosol species globally, we're exploring more emission uncertainty in the SSPs than we were in the RCPs. So we're going in the right direction. And this is true regionally as well. So 3 rows for our 3 aerosol species and columns for different regions. You can see those colours in the SSPs generally spanning a wider range than was explored in the RCPs in the grey shading. And you can see the emission uncertainty here being dominated by Africa and Asia as we go into the future. If we think about a Paris target, most of our aerosol emissions are going to be following SSP1 or SSP2 to meet those targets, so we're going to be somewhere down in the bottom end of this range. And here, if you look just at the top left panel, for example, black carbon in Africa, you can see a large difference between SSP2, our yellow line, and SSP1, our green and blue lines. And that gap between those scenarios may also be important for how we understand the role of aerosol in the near future. I'm going to show you an example of that now for Asia, where we've run experiments for absorbing aerosol and scattering aerosol, where we change the aerosol over Asia as a whole, and then repeat the experiment to change aerosol only over South Asia or East Asia, and then add the response together. Now, if the response was linear, you'd expect the top row, which shows the response to all Asia perturbation, and the bottom row, showing that linear sum, to look the same. And you see for both of these species that's not the case. So what we have here is a strongly nonlinear response to those regional aerosol changes, and that's because of the large dynamical component in the climate response to aerosol forcing. So when we change atmospheric circulation, that circulation response is interacting between these regions, so when we add those regions together, we miss some of that interaction. And those are the kind of interactions we might miss if we take a few existing scenarios and try and interpolate between them to understand what the response might be. So we really need dedicated scenarios to explore the role of aerosol on these near future timescales. And this very strongly regional response to aerosol is something that is often missed in climate risk assessments at the moment, because we have a framework that's developed to think about greenhouse gas driven near-term changes that largely fails for our regional aerosol emissions. So we use our IMs to produce emission scenarios, and we have a relatively low variety of regional aerosol emission scenarios. We're doing better, but we could do even better. These scenarios then go into our ESMs to produce climate projections, and these models still struggle to represent aerosol processes and aerosol climate interactions, and that results in very diverse responses and gives us the kind of uncertainty you saw in our effective rated forcing in the first slide in this talk. These ESM outputs are then used to either train emulators or fed directly into impact models. And at this stage, we're often still using global means or greenhouse gas pattern scaling. And you saw earlier the difference between the pattern of the response to aerosol and the pattern of the response to greenhouse gases. So there, in that step, we're largely eliminating our regional aerosol effects as well. So by the time we come to climate risk, we've often erased a lot of the regionally diverse response to aerosol. That then creates a perception that these regional aerosol changes perhaps don't matter so much, and we don't explore them with our new scenarios. So I hope today I've shown you some of the potentially large regional changes in aerosol and some of the differences between aerosol and greenhouse gases that it'd be great to explore with more diverse scenarios, particularly for the near future when we expect the largest aerosol changes to occur. So just to summarise, we think that regional climate risk due to aerosol emission changes is still a blind spot, but that near future aerosol emission changes are likely to drive strong trends in temperature and hydroclimate with a pattern that's very different to the response from greenhouse gases, simply because of where aerosol is and how it drives climate changes. And this is something that's still neglected largely in risk assessments, where aerosol is either taken as a global perturbation or treated as being something that just has a greenhouse gas-like pattern. And because of the strong nonlinearities we see in these dynamical changes to aerosol, future changes are still underexplored in current scenarios. It's not enough for us to interpolate between existing scenarios to understand regional changes. So we'd like to see in the future increased scenario diversity to help us better understand these regional patterns of response to aerosol, and also better understanding of the physics of the response to aerosol itself explored through dedicated modelling setups such as regional aerosol MIP. We'd also really love to see more pattern variability aware emulators and impact modelling to really take through that regional response to these regional changes into our risk assessments. So if you'd like to read more about this, we've just submitted a perspective article to Science, or come and talk to me at the meeting, or catch me on the online chat through June. Thanks for listening.
Sorry? Laura, are you there?
Hello.
Oh, hello. Hi, good to see you. So let's see. We have some questions for you from the audience. Yes?
Hi Laura, thanks. I think that was very important work that you're doing here, and I think it's still a blind spot. During my PhD, I was dealing with a lot of people that were proposing to leave the aerosols up there, kind of manipulate the climate that way. So maybe you could just give us a hint on what to tell those people.
So this is the geoengineering question. Geoengineering is a tricky one. There's lots of studies that show that we can put aerosol into the stratosphere and that will reduce the surface temperature. But because of the way that aerosol works, we then tend to get regional precipitation changes. So even if we can distribute the aerosol in the atmosphere in a way that gives us a uniform temperature decrease, for example, we will see precipitation changes be different regionally. So we might cause droughts or flooding in particular regions. So that gives us a particular pattern top of that, you have the additional issues of geoengineering in that when you stop, all of those potential benefits go away as well. So it's a long-term commitment that's not necessarily politically stable either.
Thank you.
Hi.
Some more?
I have the mic. Hi, this is Matthijs Harmsen from PBL. I could have two questions. First one is actually, so I totally agree, looking at these graphs, if this is neglected, that would be a problem. But could you maybe explain a bit what that would mean? So if you would have these pockets that are neglected maybe because we have the global average, what could be the problems that arise?
So the examples I've used in the talk were primarily for Asia and Africa, and we often think about the monsoon response to aerosol in these regions. Historically, aerosols accounted for more than half of the monsoon changes in these regions, and as we change the sign of the emissions, we might expect to then be adding that amount of precipitation change on top of the greenhouse gas-driven response. So by neglecting these things in assessments, we could be missing up to half of the response in the near future. So for mitigation, that's a big thing to miss.
Yeah, if I may, a short question would also be in line with what people sometimes sort of promote as an option. So black carbon is sometimes still seen as an option for mitigation to reduce climate change. If you only focus on black carbon, what are your opinions on that?
I mean, it's going to be a similar answer to the geoengineering question. Often these things only consider the temperature impacts, so that's great. But then we have these big dynamical changes in the atmospheric circulation as well that tend to bring large precipitation changes, and then you need the full modelling to understand what's going to happen regionally. And by neglecting that, you might be missing potential changes in seasonal or extreme precipitation.
Thanks.
Thank you. So I think thank you, Laura. I think you brought a very important contribution here today.
Thank you.
Thank you. Okay, I think it's time for Daniel. There you are.
Thank you. Very nice to be here. Oh, I already sort of started my presentation. So I'm going to present my work here, the social cost of methane and its sensitivity to different scenario assumptions, so a slightly changed title compared to what's in the program. And it's joint work with Jorge Garcia Martin, Christian Azar, and Thomas Sterner, and I'm personally from physical resource theory at Chalmers University in Gothenburg. And yeah, you all know methane is an important greenhouse gas. We have talked about that sort of for 1.5 hours now. This figure is from the IPCC Working Group 1 SB1 report. And you see here that sort of the past emissions of methane has increased to increasing the global mean surface temperature by 0.5 degrees Celsius roughly. So it's by clear the second most important greenhouse gas as we observed until today. So it's of course critical to do something about methane and other non-CO2 greenhouse gases. But when it comes to methane, it's a totally different beast when it comes to its atmospheric lifetime compared to CO2, as we also heard in the discussions here before. CO2 emissions are largely reversible in the atmosphere, while methane emissions sort of the concentration sort of decays with a time constant of around 10 years, and after 30-40 years it's largely gone from the atmosphere, although its temperature impacts tend to stay longer in the atmosphere. And usually when sort of comparing these gases, one looks at sort of the global warming potential and other metrics. Another way of looking at the different gases is to look at the social costs of the metrics, or of the gases, and that is what we will do in this study. So the aim of this study is to estimate the social cost of methane and as well as the social cost of carbon dioxide in a cost-benefit integrated assessment model using recent scientific knowledge on the carbon cycle, the dynamics of the temperature response, and new estimates of the damages of climate change and a choice of discount rate. So in this study, we do not sort of optimize or set the model to meet a certain target like a 1.5 or 2 degree target, but we rather find sort of the optimal of temperature range level by sort of weighing the damages of climate change against the cost of reducing the emissions of climate change. And we also do some sensitivity analysis. And also finally here, if one looks at the ratio of the social cost of methane to social cost of carbon dioxide, that is sort of equivalent as a metric and can be compared to global warming potentials. This is also something we'll do in the presentation. But first, some words on this issue of cost-benefit analysis, because it's so much more uncertain, the cost-effective scenarios, and it sort of can be criticized on many respects. I just want to say a few words on that first. So the social cost of greenhouse gases are widely used in policy assessments, for example, in the US, where it's sort of critical in policy assessments. The social cost of a greenhouse gas is the modeling the climate damage caused by one additional unit emissions of that greenhouse gas. So that's basically the definition. And cost-benefit approaches, although they are very uncertain, are sort of valuable complements to cost-effectiveness approaches, which is sort of dominating the scenario literature. And as I said before, the social cost of methane to social cost of carbon dioxide is a valuable complementary metric compared to sort of global warming potential, global temperature potential, etc. And also finally, as I said before, this issue of climate damages are very contentious. It's very hard to estimate climate damages, and one should have that in mind when interpreting results from cost-benefit analysis. Also, this choice of setting a discount rate is very sort of have strong influence of the results as well, so one should also have that in mind when interpreting results from cost-benefit analysis studies. So we use the main reason for that is sort of the change of the carbon cycle to using fair carbon, the model carbon cycling fair instead of Nordhaus standard carbon cycling, which is very pessimistic, and also the change of the energy balance model. And one can also look at other cases where we don't have any abatement at all. The CO2 emissions, of course, become much larger. It basically follows the baseline in dyes. The methane emissions also is sort of basically follow the SSP2 scenario. And you can see in the case where we have sort of no net negative emissions, we get sort of slightly more reductions of methane emissions and also more rapid reductions of carbon dioxide emissions. And sort of what you see also as well, that in the case where we don't have any net negative emissions, we get a sort of long-term level of temperature change. It never drops below sort of 1.7, 1.6, something like that. And then if you go to the social costs, and then we don't look at up to 2,200, we look at the numbers in the near term. So the scale on the x-axis here is up to 2050, and it's US dollar on the y-axis on the social cost of carbon dioxide and social cost of methane, and it's the ratio of them on the right here. And the ratio of them can be compared to the global warming potential. As you know, global warming potential 100 is 27 for methane. And the rate we see here for our social cost estimate starts around 20, so relatively close. You can also see here that the social cost estimate of carbon dioxide in this version of DICE is around $200 per ton of CO2, which can be compared to the sort of standard US estimate, which is around $40, $50 per CO2, something like that. And the main reason here is for getting a high number here is primarily due to the change of the damage function compared to what is used in the US EPA studies and also by the Biden administration. And you can also see here that the social cost of methane, basically the damages one ton of methane costs us when we made it is around $4,000, so it's a sizable number. And then if you add these alternative cases that we analyzed, you can see that the social cost estimates of especially carbon dioxide is very sensitive to your assumptions. It skyrockets in the case where we don't have any abatement at all. And the reason for that is the temperature becomes so large, so the marginal damages of one additional ton becomes very large. So you get basically very high social cost estimate of carbon dioxide, around $1,200 per ton of CO2, which is sort of huge compared to the IIASA price, which is around 80 euros per ton. You see for the social cost of methane, it's sort of less sensitive to the different assumptions. And the reason for why it's less sensitive is that it's also more short-lived. So what sort of happens in the long term within the model is not that critical for the valuation of methane, because it's largely gone, your methane emissions, when the temperature starts to get really, really high, for example, as in the base case. Or when you assume for such large discount rates as you do in the green case, the price of CO2 much more affected by that compared to the methane, due to the sort of the different nature in the lifetimes in the atmosphere. And then you also see that the ratios, they are much, even though they are sort of varying pretty much between sort of 7, so methane, same with sort of the value of methane being sort of about 7 times as high in this case where we don't have any sort of abatement at all, to around 30 times as high if you use sort of standards, Nordhaus standard assumptions, but pretty close to the global warming potential 100 in most of the cases. And
And that is sort of not a surprise. This is sort of, one can basically derive some modeling to show that the social cost ratio, social cost of methane to social cost of carbon dioxide, is fairly similar to the global warming potential under some restrictive assumptions. And especially if you sort of use this assumption of a fixed background atmosphere and also say that we have a fixed size of the economy, so it's a bit analogous to the assumption you make for global warming potentials. And you set the discount rate in the social cost estimate to be the inverse of the time horizon you use for global warming potentials. Then you get this relationship as seen here. In the blue bar you have the global warming potential for different time horizons, and then you have the social cost ratios here. When you use sort of a discount rate, it's the inverse of the time horizon in global warming potentials in the purple or grayish bar. I don't know what color it is. So it's a very strong relationship here. And then go to my final words and conclusion. So cost-benefit analysis can generate results in line with the targets in the Paris Agreement, depending on the assumptions on discount rate and damage functions. And also then, so of course, then emission pathways in line with those estimated by more technology-rich IAMs. And social cost and social cost of methane and social cost of carbon dioxide are sort of the net present value of climate damages of emissions of methane and carbon dioxide, as we just presented. These estimates are sensitive to model assumptions, for example, the discount rate and the damage function, but also to the assumption on level of abatement and abatement cost functions. We didn't really explicit here, but it's also sensitive to the abatement cost functions. And the ratio of social cost of methane to social cost of carbon are considerably less sensitive than each individual value of social cost of methane and social cost of carbon dioxide because they are sort of strongly correlated. And the numerical value of global warming potential and the ratio of the social cost of methane to social cost of carbon are relatively similar in cases where the assumptions are sort of comparable. I think this was it. This was my references, and thank you.
Thank you very much. I was wondering if you had considered using another metric than global warming potential. Like, I think the IPCC sixth assessment report now provides global warming WP star. There's global forcing equivalent, and so on and so forth. And it gives a little bit of a different picture concerning non-CO2 forcing compared to CO2.
Yeah, so basically what one can say, we don't use the metric in the modeling. So basically what this falls out that the ratio of social cost of methane to social cost of carbon dioxide is relatively similar to global warming potential. So one can see this sort of partly as an argument in favor of global warming potential because it's sort of it's a type of metric that also align with economic reasoning. For example, the global warming potential star is, I would say it's an interesting metric, but it's very difficult to integrate it in an economic way of reasoning.
Everyone, McJohn from PNNL. I really like how you upgraded, so to speak, DICE model to be more, quote, realistic. But one thing that struck me was the level of reduction in methane emissions that you have. Previous presentations on, non-CO2s and methane emissions, it's really hard to mitigate that much methane emissions unless we're killing off cows or stop eating rice. Do you have some sense of how we can accomplish that much methane mitigation?
So basically, what we did was basically use the marginal abatement cost curves from Monsoon, and I agree it's sort of relatively low emissions of methane. It goes down to sort of 100, 150 or something in the results presented. But we did compare it with the SSP2 and 1 that meets the 1.9 wet per square meter target. And for many of the more technology-rich integrated assessment models, they've sort of reached similar levels of the methane emissions. And personally, my view is also that it's probably very hard to reach those low levels without sort of certain levels of sort of dietary changes, for example, or revolutionary changes in the agricultural system. But we haven't really considered that explicitly. So we basically just use the abatement cost functions and applied it into the SSP sort of emission pathways. So Matthew says it.
Yeah, I just want to confirm that they are on the high side. teams, but yeah, there are not many teams, if not there's hardly any that make these longer term X, and so you have to be speculative, and there are definitely mistakes in there, the errors in there, but they're low, but I first of all also recognize that it's similar to what you see in other models. Maybe also because they have additional assumptions on how you can reduce, so maybe that's unrealistic too. But yeah, you can expect, I think, to go deep, especially on the fossil fuel side. And that is already a large chunk. And then the question is, yeah, the remaining parts, how optimistic can you be indeed? But we for instance, like enteric fermentation, methane, there we were a bit less optimistic. So that was probably in our default mech now, basically. Yeah.
Yeah, maybe I can. I have a question.
Yes, of course.
So for the damage function that you're using, because it seems that I mean, how do you treat the time problem there? That you could have exceedance of the temperature targets in the shorter term, which could lead to very much high damage. And then, how is this treated in the damage function?
Yes, basically the damage function is relatively simple. It's basically sort of a second degree polynomial. So your level of damage from the temperature change increases with the level of temperature change you have. So you basically compare, for example, if you take the numbers we use, the damages to the economy for sort of increasing the temperature to around 3 degrees Celsius is sort of around 6-7% of GDP, compared to Nordhaus version, which is around 2-3% of GDP. But then if you sort of decline the temperature, then sort of the damages will sort of also decline. So it follows the temperature directly in a sort of by a second degree polynomial.
Okay, so it means that you could have kind of catastrophic damages sort of in the short term if you exceed temperatures in the short term.
You can design your damage curve like that if you had information to do it.
Yeah. Okay. Yes. Okay.
Yes.
Thank you.
Thank you.
So, thank you very much. I think we have like 5 minutes left, so I would give the floor to Stefan, who has a poster. Maybe you can tell where exactly it is. Sorry.
Well, in fact, I don't even know where it's physically standing because they removed the posters, but it's online. So basically in the poster, to continue on the optimistic side, so we tried to identify a portfolio of mitigation options for the agricultural sector that would allow the sector to transition towards climate neutrality. So what we did is we used the global model, our model developed at IIASA in the IBF group, and kind of updated the representation of non-CO2 technically abatement options based on the US EPA dataset. Next to it, we have also a number of structural options in the model and demand-side options. And then we enhanced the model also with novel CO2 sequestration options on the AgLand side. So this contains like biochar application, silvipastures, and soil carbon sequestration on cropland and grasslands. And then we run a series of mitigation scenarios with the carbon price, targeting either individual sources from the agricultural side versus a joint application of the carbon price. And then looked at the results and tried to isolate effects on additional warming, but also economic effects for farmers and also on the mitigation potential, obviously. And what we see, not surprisingly, I guess, for everyone now in the room, is that methane is a big lever, so allowing to kind of achieve or stopping additional warming from agriculture sector already by 2040 with a carbon price of $100 methane plus N2O. So methane is a big lever. To combine with N2O, it allows to stop this additional warming by 2040 at $100. And if combined with CO2 sequestration efforts on AgLand, it can be even push it a bit further or kind of earlier. So by 2030 already peak additional warming plus some mitigation potential in 2050 of around 5 gigaton CO2 equivalent. So if you're interested, check out the poster, and I hope there will be a paper, well, let's see, say early next year.
Does anyone have any questions? all that we had today. I should remind everyone that the plenary sessions from this morning, they will take place at 6:15 for 1 hour in the theater tonight. So. Oh. And we can also take questions from online participators. Anyone? No. Sorry. Okay. Sounds as if it's quiet. Okay. Oh. Yang Ho? Yes? Yang Ho? You have a question?
Yes.
Sorry that we might have missed it before.
I don't have a question, I just plot.
Oh, okay. All right.